Okay, so let's get going. Right, so what I would like to do is quickly finish the solution to example 3, which we started last week, and we stop after we've determined the... I'm still here. Yeah, so we finished that particular example. We'll take about 5 to 10 minutes, and then we'll move on to the new topic. So we'll try and finish that tomorrow. So I will draw the diagram for example 3, and I will write the solution where we stopped, and then we will try to finish the rest of the particular question. So example 3 is a beam that is simply supported with an overhang, and there is a point force there, and uniformly distributed load over that section. So I will rewrite the values again. We were given Q to be 30 kilonewton per meter. P was 20 kilonewton, and this length here was given as A, and that length there was given as B. A was 4 meters, B was 1 meters, and modulus was 200 gigapascal, and I was 4 times 10 to the power minus 6 meter 4. And we will also find the magnitude of the deflection where load P is applied. So we've already done the first stage. We found the magnitude of the reaction forces, and we've determined the expression for the bending moment. So this end here we denoted by A, that we denoted by C, and that we denoted by C there. So I will write down the bending moment equation, which we derived on Thursday last week, and then we will take it from there. So we've already shown that the bending moment is 55x minus 15x squared for the section between end A and point B. So we showed that last Thursday. So if you missed the lecture last Thursday, you might want to check the solution given online. The second part, we showed that is 20x minus 100 for the section between 4 meters and 5 meters, and that is section BC. And for both our x is in meters, and m is in kilonewton meters. So now we want to find the magnitude of the deflection. So that's where we're going to start. And x in that case, the origin of x is at location A. So x origin is on the left-hand side of the beam. So now let's find the magnitude of the deflection. So because we have two bending moment equations, so we're going to do the equation twice, one for section AB and the other one for section BC, and then we will state the necessary boundary conditions to find what we don't know. So let's start for section BC. So we'll start and section AB, that's the one on the left. So we start with the deflection moment expression, d2v dx squared equals minus m all over EI. So we know what m is, so that's the one we've just stated. So I'm going to put the expression for m from that equation as 55x minus 15x squared. We do the integration once, and then we do it the second time. So we'll now say dv dx, which is the doing the first integration, minus 1 over EI. That would be 55 x squared over 2 minus 15 over 3 x cubed plus C1. And then we do the second integration. So we'll say V equals minus 1 over EI. We do the second integration. That will be 55 over 6 x cubed minus 15 over 12 x4 plus C1x plus C2. So C1 and C2 we don't know yet. So, but we'll soon find out what they are. So we go again and we look at the second part, section BC, and then we do that again. We'll say the 2V over dx squared equals minus m over EI. I will put what is the expression for the bending moment for that section, which we stated a few minutes ago. I will say minus 1 over EI. And the bending moment for that was written as 20x minus 100. So that we do the first integration and we do the second one as well. So if you do the first integration of that, we'll say dv dx equals minus 1 over EI equals 20x squared over 2 minus 100x plus, I'm going to call that D1. And then we do it the second time, and we will say we got V equals minus 1 over EI. When you do this second time, we have 20 over 6 x cubed minus 100 x squared over 2 plus D1x plus D2. So we have four unknowns. So let's just state again that the first one is only valid between 0 and 4 meters, because that is that particular section, and this second one is only valid between 4 meters and x and 5 meters. So but from what we've got now, so we cannot find the magnitude of the deflection of the beam, which is V, unless we know what C1 is, and C2 is, D1 and D2 as well. So we now need to apply our known boundary conditions. So with the number of unknowns, so how many conditions do we need to find all the parameters that we don't know? 3? So there are 4 things that we don't know. We don't know C1, we don't know C2, we don't know D1, we don't know D2. So if there are 4 unknowns, we need 4 separate boundary conditions. So if we go back to the beam, which I'm going to show again, and we can look at what we know and what we don't know. I'm going to put that aside quickly. So our x starts from here. So we know that is simple support. There will be no movement of that point. So the first condition will be that when x equals 0, the magnitude of the deflection at that point will have to be 0. And when x equals 4 meters, which is this point, the magnitude of the movement will have to be 0 at the same time. So we've got 2 there, and then I will explain how we find the next one. So let's start from those 2. So within the first section AB, I'm going to apply those 2, and then we'll see what that will give us. So the first condition is what happened at point A. So we start and we'll say condition number 1, that V equals 0 at x equals 0. And we'll put that in that equation. So because it's for section A, I can do that. I will say V at x equals 0. Therefore, 0 equals 0 plus 0 plus C2, which implies C2 equals 0. And if you want to check why that is so, I will just go back again. That is the equation that we are using. So x equals 0, that term is 0, that term is 0, that term is 0. It's only C2. It's only C2 that is left. So we've got that. So we know what C2 is, so we've got the first one. Then we go and do the next one, which is point B. I will say V equals 0 at x equals A equals 4 meters. I will go back again and make x equals 4 meters because at the point of support, there is no movement of the beam. So we'll do that again. We'll put V at x equals 4 meters. So I'll make x equals 4. In that equation, I have 1 over EI. So what we need to do now is to go back there, and instead of x cubed, I have 4 cubed. 4 raised to the power 4, I have 4 here. C2 is already known to be 0. So if we were to do that, I will end up with 55 over 6 x cubed minus 15 over 12. So that will be 4 now. Since we know it is 4, that will be 4 raised to the power 4. And then plus 4 C1. Yep.
If 4 belongs to both of the sides, can I use the second equation as well?
Don't worry. So you will see how we do that. Remember, we need 4 set of conditions. So we've only done 2 here, and then we'll go back and use the second one for section BC. So if we are to do that, if you simplify that, what you will get will be minus 1 over EI 3520 over 6 minus 3840 over 12 plus 4 C1. Okay? Yeah.
So in the second condition, you said that C2 is equal to 0.
Yeah.
So it's fixed all the time.
Sorry, it's what?
C2 is fixed all the time, it's equal to 0.
No, C2 is 0 based on this particular condition.
Yeah.
Okay, yeah.
So it doesn't change with the change of x.
Yeah, you don't assume a particular constant is 0, you go with the particular problem you've got. Okay, right. Sometimes it's not 0. You will see when we do this now, C1 will not be 0. Okay. Right, so if you try to rearrange that, remember the left-hand side is 0, so we can show that C1 here will be around 200 over 3 EI. So now we know two of the 4. To go back to the question you asked a few minutes ago, I now need to find what is the remaining 2. So I go back to what I've got, which is, if I show the diagram again, let me just go back. So we've just looked at what is happening in this part of the beam. So I have another equation for this part of the beam, but this point B is shared between this one and that one. So if I calculate the magnitude of the deflection using the equation from this side at point B, I must get the same magnitude if I calculate what is happening at point B using this one. So because point B is shared between the 2 of them. So I will go back and I will say, my number 3 is that whatever happened at point B from one side to the other has to be continuous. So I will say dV dx at x equals 4 meters for section AB must be dV dx at x equals 4 meters for section BC. Because you are looking at the same point, it doesn't matter which of the 2 equations that you use, you must get the same number. So if we are to do that, so I can now put that in, and that will give me one of the 2 constants for D1 and D2. So if I did that, what I would get would be minus 1 over EI 55 over 2 times 4 squared minus 15 over 3 times 4 cube equals plus 200 over 3 EI equals minus 1 over EI 10 times 4 squared minus 100 times 4 plus D1. And then with that, you can find D1 because everything there is just constant. D1 is the only thing that we don't know. If you do your simple algebra correctly, you will get D1 equals minus 800 all over 3 EI. So I have C1, I have C2, I have D1, I have one more constant, and the second constant will be what you asked before. I'll make what is the magnitude of the deflection at point B using the second equation. So we go and apply this last set of boundary condition, and I will say number 4, that V equals 0 at X equals 4 meters for section BC. And if you are to do that, you will get the last one. So let me just so to do that, we have V at X equals 4 meters equals minus 1 over EI 20 all over 6 4 raised to power 3 minus 50 times 4 raised to power 2 minus 800 over 3 EI times 4 plus D2. And I can find D2 there. So so because everything here is 0. So if you try to solve for D2 and your basic algebra is still right, so you should be able to get D2 equals 1720 all over 3 EI. So the four basic constants, so let me just write them back again. I will start with the first one, C1 and C2. We've now shown that C1 equals 200 over 3 EI. We've shown that C2 is 0. And we've shown that D1 equals minus 800 all over 3 EI. And D2 equals 1720 all over 3 EI. Now I can put all of that back into the equation for the expression for the deflection for the two sections and also equation for the slope. But I will do it for the deflection, and then I will show what the value is at the end where the load P is actually applied. So let's write the final solution. So for section AB, so that is where you have the uniformly distributed load. So if we substitute all those constants, what you will get is that V equals minus 1 over EI, 55 over 6 X cube, minus 5 over 4 X4, minus 200 over 3X, where X goes from 0 to 4 meters. If you look at section BC, which is the second one, then V can be shown to be 1 over EI, 20 over 6 X cubed, minus 50 X squared, plus 80 all over 3X, minus 1720 over 3. In this case, X goes from 4 meters to 5 meters. So now if I want to find the magnitude of the deflection at turning distance X from A, all I need to ask myself, what is the value of X? How far is that point from point A? And that will determine what X is. So if you want to find the magnitude of deflection at 2 meters away from where the load, where the support is, I will make X equals 2 meters, and that will tell me what the actual magnitude of the movement of the beam is. So Units are very important. So what we've adopted here is that x here is in meters. That's what we've chosen. Our I is in meter 4, and modulus, because we chose our load in terms of kilonewton, the modulus in this case is in kilonewton per meter squared as well. Now I want to put in some numbers, which is the numbers we are given. We know E, we are given that. We know I, we are given that. And we want to find the magnitude of the deflection where load P is applied. So if you go back again to the diagram, we see where load P is applied. So let me just show that again. So that is load P right end there. Our reference is this. So what will be x at that point? So what will be the value of x where P is? 5. So if we want to find that, I need to put x equals 5. And which of the two equations should we use? Is it this or this? This second one. So we go now, and I'm going to use that second one, and I'm going to put x equals 5. So I know my modulus. Remember, modulus has to be in kilonewton per meter squared. And I know my I. I can find the value of the movement at point P. If your deflection is positive, it means that point is moving downwards. If it is negative, it means it is moving upwards. And you will see when we do this, that value is going to be a negative value. So, and there's a reason for that because of the way the loads are put on that P. So let's try and do that. So at point P, S equals 5 meters. But we already know that P is given because we've already used that P is 20 kilonewton. I is 4 times 10 to the power 6, meter 4. And Young's modulus is given as 200 gigapascal. So what will my modulus be if I want to write it as kilonewton per meter squared? Maybe I should first ask, what is gigapascal? 9, okay. So we say this is 200 times 10 to the power 9 Newton per meter squared. Now I want to write it as kilonewton per meter squared. What should I write? Pascal. This is what we call Pascal. This is the same thing as Pascal. 10 to the power 6. Great. Thank you. So what we now have, I'll say 2 times 10 to the power 6 kilonewton per meter squared. So when I go to make my substitution, I will make x equals 5. I will make I equals 4 10 to the power minus 6. And I will make E equals 200 times 10 to the power 6 there. So if you go back to the equation, I'm going to go bring that back up so that you'll see how we do that. So see, we can see that. Right. So this is the one we are using. So I'm going to make my V 1 over 2 EI, and I'm going to put x equals 5. So I now have V at x equals 5 meters. What we will now have is minus 1 all over 200 times 10 to the power 6 times 4 times 10 to the power minus 6. So that is my EI. And then I'm going to put all the other values in. So I'll have 20 over 6 times 5 raised to the power 3 minus 50 times 5 raised to the power 2 plus 80 all over 3 times 5 minus 1720 all over 3. And then the rest is just number crunching. So if we're to do that, we're going to end up with something that looks like, I think it's minus 0.075 meters, which is minus 75 millimeters. So that point C will move up by that much. And I will make a sketch later on to show why that's the case. If we want to find what is the slope of location C, So I'll say slope at C. So we need to find what is dv dx at x equals 5 meters. So I'll go back to the equation for the magnitude of the deflection for section BC, and we'll be able to do that. So I'm going to do that here. I'm going to write that will be minus 1 over EI 60 all over 6 x squared minus 100x plus 880 all over 3. Now I can put x equals 5 meters there, and then I'll be able to find that. So that's the slope. That will be minus 0.054 radians. So when you get that, because that's the slope, so that is in radians. If you convert it to angle, so you get roughly minus 3.1 degrees. So both the deflection and the slope at that point are both negative, and I'm going to show why that's the case. So I'll show the beam again, and I'll show you why that's the case. Right, so are we okay with that?
How did you know that was the radian?
Sorry?
How did you know that was the radian?
Because the slope, I will show that. The slope is the angle that the tangent makes with your horizontal x-axis. Yeah. Yeah, so in every engineering problem, when you see angle, they are in radians. Yeah. So let's look at why it's like that. So let's just say that's the beam. That is A, that is B, and that is C. So the first one I'm going to do is, let us assume, remember we had a force there. I'm going to assume that I didn't have that force first. Let's just see what we have when you have this. So if the loading was just like that, what's going to happen is that when that beam deforms, the film is going to deform like this. That's the way the beam will deform, assuming there's no point load there. If you now put a point load, the effect of the point load is to move this one here slightly downwards. So if I redraw that again and say I've got A and I've got B and I've got C there, and I've got uniformly distributed load like that, and I've got a point load like that. So we'll still have something close to that, but the deflection will not be as huge. We now have that, and this will go like that. Because the force, that point P, will push that end downwards a little bit. So this distance here, that distance there is the one that we have just determined to be, 75 millimeters. 75 millimeters. So that would be 75 millimeters. Because it's been pushed up from where it was before. And the slope, which I showed to be negative, so it is this slope here, like this. If I draw a line like that at that, so that angle is the angle going that way. That's the slope. That is, what's the angle? I think it's 3.1 degrees. That is 3.1 degrees. So if that slope was a positive number, then it means that your slope is like that, and you are going that way. Okay, so that is all. Yep.
How did you know that the negative will give the positive deflection? I'm sorry, that the negative deflection will be above the x-axis, basically.
Because that's the convention we chose. We said our x is pointing from the left to the right, and our y is pointing downwards. If you go back to the start of the first derivation that we did, yeah.
And about the boundaries, can we choose different boundaries as well? If we know that the deflection, when deflection equals 0,
Yeah.
the angle will also equal 0. So can we set this
No. No. No, not at the support. Not at the support. So for example, if you look at that here, if you look at that deflection is 0, but the slope there is not 0. If I draw a tangent to this, right there, I'm not going to get 0.
Where can you use that relationship?
Which relationship are you referring to?
Where df over, where the first integration will equal 0 and v equals 0 at the same time. There was one example we did it and I can't find it now. When the deflection and the slope are equal 0 at the same time, in the same place.
That is, but maybe that's because you have a built-in, you have a beam that is built in like that. If you have a beam that is built in like that, so at this point here, that beam cannot deflect and it cannot rotate. Okay? So you take every problem separately. So don't try to memorize any particular boundary condition. Boundary condition will depend on the nature of the problem that you've got. But at the support, if you have a simply supported beam, that is the role of the support. The support is to stop the movement of the beam. Okay, so any questions? Because I want to change to a new topic. Right? Are we okay? Questions?
Can I see the first page that you put up?
Which first page are you referring to now? There are so many pages.
Page with the diagram.
Of the diagram.
Yes.
Remember, this is the continuation of what we started on. Yeah. Okay. Good. So let's move on to the new topic. So I'm going to quickly change this.